And we are back to finish off Chapter 10 of Pre-Calculus Made Difficult. We've seen, last time, that our original definitions of sine and cosine, which applied only to acute angles, could be extended in a clever way to the unit circle, so that sine and cosine now apply to any angle whatsoever, including negative angles. And this extension of the domain of sine and cosine remained very geometric. Instead of triangles, we now have circles, and even waves once we start looking at graphs. But geometry remained in the forefront. So far, so good. But if you look in most textbooks on this subject, once they've reached this point, and it is time to extend the domain of the tangent, you will find that they typically drop the geometric approach altogether. And what they do is simply define the tangent of theta when theta is beyond that first quadrant. They simply define it as the sine over the cosine, an identity which we know holds in the first quadrant, that is for acute angles, because we proved it there in the original context of right triangles. And logically, that's a perfectly legitimate way to go. And if you wanted to know, for example, what is the tangent of 180 degrees, well, you would just appeal to this definition. You would say, by definition, tangent of 180 is sine of 180 over cosine of 180, and those are each values you can read off the unit circle, since you know how sine and cosine are defined. If we start at the usual place, rotate 180 degrees, what do we get? The sine of 180 is the y-coordinate of that point, which is 0. Cosine of 180 is the x-coordinate, which is -1. So this would be 0 over -1, which of course is 0. And that's it. We have found the value of tangent 180 degrees. So that's a perfectly valid approach. However, it is possible to make geometric sense of tangent on the unit circle. And I think that brings you a lot more insight. Surprisingly few people seem to see this in trigonometry classes. In fact, I'm going to show you two different ways that you can see the tangent of theta on the unit circle. And just as importantly, the first way I'll show you will explain why the tangent function is called tangent. I hope you found that understanding why cosine is called cosine helped you grasp the nature of that function. I think the same thing will be true of tangent, and it's very easy to understand. So let's start with our unit circle. We have our angle theta through which we have rotated, and let's just start in this first comfortable quadrant. If the point is in this position, its coordinates, of course, we know are cosine theta, sine theta. So if I drop a perpendicular, then I know the legs of this triangle are going to be cosine theta and sine theta. Now here's something interesting. At point 1, 0, our usual starting point for our rotations, I want to draw the tangent line to the circle. Literally the tangent line. The line touching the circle at that one point. Oh, a literal tangent in the discussion of the tangent function. This promises to be interesting. What will happen next? Well, take this radius of the unit circle and extend it until it hits the tangent line. When we do that, we get this new right triangle. It's a right triangle because of the well-known geometric fact that if we have a circle and a radius of that circle and the tangent line drawn to the circle at the point where the radius meets the circumference of the circle, then the radius and the tangent are always perpendicular. You will have seen this already in chapter 9 of the book. Exercise 33 in that chapter, to be exact. This is a useful fact for many reasons, but in the context of trigonometry, it's useful because it's a way of bringing right angles into a picture involving circles, and where there are right angles, there are, of course, right triangles, and where there are right triangles, well, there is, obviously, trigonometry. But anyway, here we have these two nested right triangles, and of course, they are similar to one another by angle. They both share angle theta, and they both have a right angle. Let's put that similarity to use. I'm interested in the length of this leg of that new right triangle, is tangent to the circle. Let's call it x for now. Because of our similar triangles, I should be able to figure out what x is. In particular, x is one leg on this triangle, but another leg on that triangle, we know, obviously has a length of 1, because it is a radius of the unit circle. Anyway, by similar triangles, we see that x is to 1 as what is to what? Well, let's see. That x is to 1, that is on our big right triangle. That's the leg opposite theta over the leg adjacent to theta. So x over 1 should be equal to the corresponding ratio on the smaller but similar right triangle. And there, the leg opposite theta is sine, and the leg adjacent to theta is cosine. So x is to 1 as sine is to cosine. Hey, but sine over cosine, as I just reminded you a moment ago, is tangent of theta. So x over 1, or in other words, x, is the tangent of theta. That is, this length, which is literally tangent to the unit circle, is tangent theta. Aha! And now you see why tangent is an appropriate name for this particular trig function. It measures a length on a literal tangent. And we can take this idea and generalize it and take it as our means of extending the domain of tangent beyond acute angle. And just as we defined cosine and sine for any value of theta to be the coordinates of this point, we can define tangent for any value of theta to be a coordinate, namely the second coordinate, of this point, though it takes a little care to think about what that would mean as our angle theta goes into other quadrants of our unit circle. I write this all down in full detail in the book, but here I just want to give an example or two to show how it works. So for example, let's say we were considering the tangent of 135 degrees, and we wanted to reason this out on the unit circle. Well, let's draw a quick sketch. 135 degrees is a nice angle. It's a right angle, 90 degrees, plus another 45 degrees. So there's our 135 degree angle. Now the way we can see tangent of 135 degrees, this first way anyway, is to think about that tangent, always drawn through that point 1, 0. And then we just have to ask ourselves, okay, I've got the radius in the position I want, and I just have to extend the radius until it hits the tangent line. Well, in this case, I have to extend the radius backwards to do that, like so. And we define the tangent of 135 degrees to be the y-coordinate of this point, where the extended radius hits the tangent. So what does that tell us? If nothing else, we know that the tangent of 135 degrees is going to be negative, because obviously the y-coordinate of that point is negative. But what will it be? Well, we can still use the same kind of trick we used with sine and cosine, all those reference angles. If we have 135 degrees here, we looked at the so-called reference angle, the acute angle that the radius makes with the horizontal axis. In this case, that would be 45 degrees, and it's a reference angle in the sense that we can refer that angle back into the first quadrant, where we are very, very comfortable, because that is where SOHCAHTOA is in his heaven and all is right with the world. And we can just think about what's going on in that first quadrant. Because if we think about 45 degrees over here, well, my drawing is not very good, but the idea is that this triangle and this triangle are congruent, despite appearances, which means that if I'm interested in the y-coordinate of this point, I can just think about the y-coordinate of this point. What do I know about the relationship between their y-coordinates? Well, of course, they're equal but opposite. They have the same magnitude, but one is positive and the other is a negative. And the y-coordinate of this point, by our extended definition of tangent, that's the tangent of 45 degrees. So y-coordinate here, tangent of 45. Y-coordinate of here is the tangent of 135. So tangent of 135 and tangent of 45 are equal but opposite. And of course, tangent of 45 degrees, as everybody knows, is 1. So we are done. We have the tangent of 135 degrees is equal to -1, which looks entirely plausible, right? If we rotate through 135 degrees, where does that radius meet that tangent? Right here. That looks like the second coordinate is -1. Good. Now, of course, you could also have found this exact value by noting that tangent of 135 is sine of 135 over cosine of 135, using that identity, or definition in this extended sense, and then figuring out each one of those separately by once again thinking about 135 degrees on the unit circle, and we could say sine of 135, that's the y-coordinate of this point, which is the same as has the y-coordinate of this point, which is the sine of 45 degrees, which is 1 over root 2, and cosine of 135. Well, let's see, that's the x-coordinate of this point, which is equal but opposite to the x-coordinate of this point, which is the cosine of 45 degrees. So since they're equal but opposite, cosine of 135 would be minus 1 over root 2, and then we would get minus 1, which of course agrees with what we saw the other way. Both approaches are fine. I think this one is a little cleaner once you get used to it, and I will show you a third way very soon when we get to our second interpretation of tangent on the unit circle. But for now, I just wanted to show you how it works. Let's do one more example. How about the tangent of 210 degrees? All right, let's think it through on the unit circle. 210 degrees, that's 180 plus another 30. So something like that. And of course, my reference angle is going to be 30 degrees. So I'm going to think about that angle in the first quadrant. Now I'm thinking about tangent. So I've got to think about this tangent line. What is the tangent of 210 degrees? Well, I rotate here. Here's my radius. I extend it until it hits the tangent line, which is going to be all the way back here. And the second coordinate of that point, the y-coordinate, is going to be tangent of 210. But hey, look, if I just looked at the tangent of 30 degrees, so I extended that radius until I hit the tangent line, it hits in the exact same place. So the tangent of 30 degrees would be the second coordinate of that same point. So that means the tangent of 210 and the tangent of 30 degrees are equal. And hopefully by now you know that the tangent of 30 degrees is 1 over root 3. And if you still don't have that fact memorized, you could always recover it by reminding yourself what a 30, 60, 90 triangle looks like, and that the ratios of its sides will be this. If the short leg is 1, the hypotenuse is 2, thanks to that equilateral triangle right there. And so by the Pythagorean theorem, the remaining leg must be root 3. Thus the tangent of 30 degrees is opposite over adjacent, which is 1 over root 3. But it's nice to just know off the top of your head that tangent of 30 is 1 over root 3. But as I've said many times, you should know where that fact comes from too. Okay, I think you get the idea of how we can extend the domain of tangent by defining tangent to be the second coordinate of that point where the radius crosses the tangent at 1, 0. So I think it is high time that I introduce you to the second way to see tangent of theta on the unit circle. So here's our unit circle. And of course, if we've rotated counterclockwise through an angle of theta, we know the coordinates of our moving point on the circumference will be cosine theta, sine theta. And as silly as it might seem to point it out explicitly, I'm just going to remind you that the coordinates of the origin are 0 and 0. I put the coordinates of both these points on here explicitly because they will help us compute something, namely the slope of this radius that's been rotated through an angle of theta. Given any 2 points' coordinates, of course you know how to compute the slope of the line that runs through them. That's baby stuff. Algebra 1. The slope is the rise over the run. In other words, the change in y over the change in x. Well, what's the change in y here as we go, say, from the origin to this point? Well, we went from 0 to sine theta. So that's going to be sine theta minus 0, or in other words, sine theta. All right, and what about change in x? Well, x changes from 0 to cosine theta. So the change in x is cosine theta minus 0, which is better known as cosine theta. Oh, and lo and behold, we have sine over cosine, which of course is tangent of theta. So look at what we have found. The slope of that radius, when we have rotated it through an angle of theta, is tangent theta. Let's clear out this intermediate stuff so that we may gloat over our interesting conclusion here. The tangent of any angle theta is itself the slope of a certain line. So we can see a few values right away. For instance, what's the tangent of 0 degrees? Well, if we don't rotate the radius at all, what's the slope of that line? Of course, the slope is 0. There's no rise, no matter how far we run. It's a horizontal line. So the tangent of 0 is going to be 0. Of course, we could also see that by thinking about that tangent line. Where does the radius cross that tangent line? What's the second coordinate there? The second coordinate is 0. So that way, too, we could see tangent 0 is 0. Or we could say, what's tangent 0? It's sine 0 over cosine 0. But sine 0 is 0, while cosine 0 is 1. 0 over 1 is 0. So lots of ways of seeing the same thing. But I like the very directness of this slope picture. Or, for example, one that you know already, but now you can see it in a different way, tangent of 45 degrees. Well, one way of thinking about that is if we rotate through 45 degrees, Of course, if we go 45 degrees, we've got that line that's splitting that first quadrant in half. It's the line y equals x. What's its slope? Obviously, its slope is 1, which agrees with the fact that, of course, you already have in your memory. Tangent of 45 degrees is 1, which you can see immediately from SOHCAHTOA. Opposite over adjacent is 1, because those two sides are equal. If I've said it once, I've said it 1,000 times. To understand trigonometry means to be able to think about the same thing in many different ways, to be able to move around it and look at it from different angles. How about this? Let's go back to tangent of 135 degrees, which we considered before. That's really easy to understand from this slope perspective. 135 degrees, that's a right angle plus another 45 degrees. What's the slope of that radius? Obviously, that's -1, and we are done. If we tried to do tangent of 210 degrees like this, what would happen? Well, we want tangent of 210. 210 is 180, that's a half turn, plus another 30. The tangent of 210 is the slope of this radius. So we can see, for example, it's definitely got a positive slope, so we know the tangent is positive, but what's the slope of that thing? You could, once again, relate it to something in the first quadrant. We have that reference angle of 30 degrees, so we could go up here, think about this business. Obviously, the slope of this radius and the slope of this radius are equal. Tangent of 210 is clearly going to be the same as the tangent of 30 degrees because these are equal. They are literally part of the same line, so they have the same slope. And tangent of 30 degrees, as we said before, is 1 over root 3. Let's do one more like this. How about tangent of 300 degrees? Well, that falls short of a full rotation by 60 degrees. That would be our reference angle for our 300-degree angle. Will that help us? It will, because we know the tangent of 300 degrees is the slope of this line. Well, what's the slope of that line? Well, let's refer it back to something in the first quadrant. Our reference angle is 60 degrees, so thinking about that radius. Well, let's see. Is there a relationship between the slope of this radius and the slope of this other radius? Yes, they're definitely negatives of each other. In the top one, for every unit we go to the right, for every unit we run, we rise a certain amount, while on the bottom one, for every unit we go to the right, we fall by the exact same amount. So their slopes are equal but opposite. The slope of this one is tangent of 300. The slope of this one is tangent of 60. So I could say tangent of 300 is minus tangent of 60, and tangent of 60, hopefully you know, is root 3. So tangent of 300 is minus root 3. And we're done. Those finding of exact values, as I said, is kind of a rite of passage in a trig class. You'll use it in subsequent classes as well. It's important that you be able to do it, but it's not in any sense deep. It's important only because you draw on deeper knowledge to come up with those values. Of the two ways we have seen to see tangent on the unit circle, I treasure the first one for explaining why tangent is called tangent, and for another reason I'll show you in a little bit. And I treasure this second one because I think it gives you a very easy way to understand the graph of the tangent function, which does not look like the sine wave. Let's talk about that next. So we want the graph of y equals tangent theta. It's pretty easy to come up with this graph if we think about either of the geometric interpretations of the tangent function. In the book, I don't even mention these graphs until chapter 12, but it's such a nice application of that slope interpretation of tangent that I can't resist showing it to you here, since you can come up with it so quickly. Okay, so when theta is 0, what's the tangent? Of course, we said already, tangent of 0 is 0, so the graph of tangent passes through the origin. Now, as we increase theta from 0 up to 90 degrees, what happens to the slope, which is, of course, the tangent? Well, the slope starts increasing, increases more. By the time we get to 45 degrees, the slope is 1, and then it really starts taking off. Somewhere it's 5, somewhere it's 10, and we are rapidly approaching a vertical line, which has no slope, or it has an infinite slope, right? When we have a 89.999 degree angle or something like that, then for every 1 unit we run, we have to rise many units to get back on that radius. So the slope approaches infinity as theta approaches 90 degrees. So on my graph, I would have this vertical asymptote, and the graph would take off like this. What happens when theta is 90 degrees? Well, then the slope, in a sense, is infinity. More precisely, it isn't defined. There is no slope, because when you run 1 unit, there is no number of units you can rise to get back onto the thing, which means that tangent is not defined at 90 degrees. And that's not too surprising, because we can think of tangent, remember, as sine over cosine. And what is cosine of 90 degrees? Cosine of 90 degrees, that is the x-coordinate of that point, which is 0. And we cannot divide by 0. So that's another way of seeing that tangent is undefined at 90 degrees. Anyway, before we go past that point, let's think about what happens if we go the other way. If we start at theta equals 0 and let it drop down to minus 90 degrees, what happens to the tangent? Well, what happens to the slope? We start getting a negative slope. First slightly negative, then more negative. By the time we get to minus 45 degrees, we've got a slope of minus 1. We quickly hit a slope of minus 2, minus 5, minus 10, minus 1,000,000. We're approaching negative infinity. So over on this side of the graph, we would have another vertical asymptote, and the graph would look like this. Now, what happens if we went past 90 degrees? Popped out on the other side here, where theta is a bit more than 90 degrees. Well, now we've got a slope that is extremely non-negative. Like maybe that's minus 10 or something. And if we were even closer to 90 degrees on the other side, maybe we'd have minus 100 slope. Anyway, so we would be going from slopes of essentially negative infinity, as it were, huge negative numbers, down to modest negative numbers, eventually to minus 1, and then all the way down, or rather up, to 0. So what would that look like on our graph? Well, as theta goes from 90 to 180, the graph would come screaming up from minus infinity towards 0. And then as we went from 180 through this next quadrant to 270, the slope would be rising up from 0 through positive values. These are all positive slopes. From 0, when we get to 225 degrees, we'd have a slope of 1, and we are approaching a slope of infinity again. So in our graph, that would look like this, and so on to the right, and so on to the left. This pattern gets repeated over and over and over again. Anyway, we will revisit this in chapter 12. The point I want to make is it's very easy to see why tangent has a weird graph like this when you understand how to interpret it geometrically. If you just know tangent as sine over cosine, it's much harder to understand where this graph comes from. You can do it, of course, but it takes more work and it's not nearly as intuitive. Okay, so now we know how to understand sine, cosine, and tangent on the unit circle in two different ways in the case of tangent. What about the reciprocal trig functions? Can they be understood on the unit circle? They can, in fact, but because they are not the most important functions in the world, I'm not going to do that here. With one exception, which I will show you in a minute when I return to the Pythagorean identities. But for the sake of expediency, I am going to take the definitions of the reciprocal trig functions that we learned back when we were dealing with right triangles, and declare that these will be the definitions of the reciprocal trig functions for any values of theta. So if we want to know the secant of 135 degrees, we would just think, well, that's the reciprocal of cosine of 135 degrees. And what's the cosine of 135 degrees? Well, we just have to think about where that lives on the unit circle. That's a right angle plus another 45 degrees, and our reference angle is thus 45 degrees. So I should be able to relate it to something having to do with 45 degrees. Cosine of 135 is the x-coordinate of this point, which is clearly equal but opposite to the x-coordinate of this point, which is the cosine of 45 degrees. So cosine of 135 is minus cosine of 45 degrees, and we want the reciprocal of that. Everybody knows that the cosine of 45 degrees is 1 over root 2. Take its reciprocal, and don't forget that negative, and we get the square root of 2 negated. So minus square root of 2. Easy? Easy. But I did say that I would show you at least one interpretation of a reciprocal trig function on the unit circle. Even though for the most part, these really aren't important, this one I think does throw some interesting light on a Pythagorean identity. So let's go back to the unit circle. We know that for any angle theta, even if theta is not an acute angle, we know the coordinates of that point are cosine theta and sine theta. But of course we know, just from basic coordinate geometry, that if we have a point on a curve, its coordinates satisfy the equation of the curve. Well, what's the equation of this circle? Everybody knows the unit circle's equation is x squared plus y squared is 1. It's the circle with a radius 1 centered at 0, 0. So that means no matter what theta is, no matter where this point lies on the circle, these coordinates satisfy this equation. Well, what does that mean? That means if I pop this in for x and this in for y, I get cosine squared x plus sine squared x is 1. Hooray! It's the Pythagorean identity. And it's very nice to connect it to the equation of the unit circle because we see immediately that the Pythagorean identity holds for all values of theta, not just those that are in the first quadrant, not just acute angles. And as we saw before, when we first met this identity, we can extract two minor identities from it by dividing both sides by either one of these terms on the left. And the one that is the more useful of the two, we get by dividing both sides of this equation by cosine squared. If we divide the left side of this equation by cosine squared, we get 1 plus, then what? Sine squared over cosine squared, which is sine over cosine squared, which is tangent squared. And then when we divide the right-hand side by cosine squared, we get 1 over cosine squared, which is 1 over cosine squared, which is, of course, secant squared. So here's our main Pythagorean identity. It holds for all values of theta. And here is our alternative Pythagorean identity, which also holds for all values of theta, or at least wherever these expressions are defined. As we've seen, for certain values of theta, tangent isn't even defined. Same holds for secant. But wherever those functions are defined, this holds too. And I'm not even going to bother with the third Pythagorean identity, which we get by dividing both sides of the main identity by sine squared, because that one doesn't come in nearly as handy. I bring it back up both to show you that they still hold in this wider context, and to show you an interesting way to remember this second identity. Because when I first introduced it, I told you that it's really easy to forget the exact form. I used to forget it all the time. And so whenever I needed it, I did have to, in my head, divide by cosine squared on both sides of the original to get it, which is fine. It only takes a second. But then I learned that there is a nice geometric interpretation of this identity, which you can see on the unit circle. So I'm going to show you that. And this is going to be much easier to see if I move my point back to the first quadrant. This will work in other quadrants as well, but it requires some finesse, and I'm just trying to get the main idea across here. So we have our angle theta. We know, of course, that if I drop this perpendicular, then the legs of this right triangle are going to be sine and cosine. And of course, the hypotenuse is 1, because it's a radius of the unit circle. We also now know that if we extend this radius until it meets this tangent line, then in this new larger right triangle, which is similar to our original smaller one, this leg opposite theta is tangent theta. And of course we know the other leg of that triangle is 1, again because it's a radius of the unit circle. Well, I want to use the similarity of these two right triangles to learn about the hypotenuse of the big triangle. If temporarily we were to call it x, then by similar triangles, we would know that x is to 1, a ratio I can see on my big triangle because the hypotenuse is x, and this leg adjacent to theta is 1. X over 1, which of course is just x, is going to be equal to the corresponding ratio, hypotenuse to adjacent, on the small triangle. But on the small triangle, the hypotenuse to adjacent ratio is 1 to cosine. And 1 to cosine, of course, is, by definition, secant of theta. Ho, ho, ho! Look what we've just established. X, this hypotenuse of our big triangle, is the secant of theta. Now, this is interesting for a few reasons. First of all, call in our friend Pythagoras. Mr. Pythagoras, what do you see on this large right triangle? I see, says he, that 1 squared, that is to say 1, plus tangent squared, must be equal to secant squared. And of course, that is exactly our second Pythagorean identity. Very nice. We saw something kind of like this earlier, but now I can give you extra piece of information now that we have connected this to the unit circle. We've discussed why cosine is called cosine, and we've discussed why tangent is called tangent. But why is secant called secant? We need a very brief excursion into Latin. So, two Latin infinitives, tangere and secare. These are the sources of these names. Now, tangere means to touch. And of course, you know English cognates like tangent itself, in the geometric sense, or tangible. But secare is not one that is as widely known. It means to cut. We do, in fact, have plenty of English cognates, though, like to dissect, to intersect, and so on. Now, think about this large triangle, the large right triangle, and think about this vertex at the top. Connected to it, we have two sides, one of which touches the circle, that's tangent, and one of which cuts the circle, that is secant. So tangent is the touching side, secant is the cutting side. Aha! That makes some sense. And not only does it make sense linguistically, why we call this thing secant, but it can help you, it certainly helps me, remember the exact form of this Pythagorean identity. Because in the old days, before I realized this, I would get confused. I knew there was a 1 in there and a tangent squared and a secant squared, but if I hadn't used it in a while, I might think, well, what is it? Is it 1 plus tangent squared is secant squared? Or 1 plus secant squared is tangent squared? And I could never remember which was which. But now I can just think of this particular triangle in my mind, and it's obvious. The hypotenuse is the one that cuts the circle. It's the secant. That means it's going to be all by itself on one side of the equation. 1 squared plus tangent squared is secant squared. So that may or may not help you remember it, but it certainly helps me remember it. And whether or not it helps you remember it, it's good to understand where secant comes from. You can, in fact, extend the definition of secant in a geometric sense into the other quadrants. You just have to watch out for where it's positive and where it's negative. And as I say, it's not really worth it because there's only so much time you want to spend with the reciprocal trig functions. It is also possible to identify cosecant and cotangent on the unit circle, but I'm not going to bother with that either. Okay, there is one last topic I need to talk about in this lecture. You've met a lot of trig identities already. The cofunction identities, the Pythagorean identities, and a few others here and there, such as tangent is sine over cosine, which is the sort of thing you should have firmly in memory, or sine of 180 minus theta is sine theta, which is the sort of thing you do not need to memorize, but rather which you can recover by drawing a picture very rapidly and just thinking about the meaning of that statement. But I need to introduce a few more very simple identities, but surprisingly powerful ones. And a lot of the power you will see, especially when you get into calculus. These are not even so much identities as properties of the trig functions, though we could express them in the form of identities. What we need to talk about are what are called even functions and odd functions. A function f is said to be an even function if a certain relationship holds between f of minus x and f of x for all x. Namely, if these two expressions are always equal. Quick example, f of x equals x squared is an even function. The squaring function is an even function because if I square, say, 6 and I square negative 6, of course I get the same thing, I get 36. If I square minus 9, I get the same thing as if I had squared 9, I get 81. Here's another one. G of x is x to the 4th plus 3. You might say, is that an even function? Maybe it's not so obvious. You can think of specific examples. Is g of minus 2 the same as g of 2? Well, let's see. G of minus 2 would be the 4th power of minus 2, which is 16, plus 3, which is 19. G of 2 would be the 4th power of 2, which is 16, plus 3 is 19. Okay, it checks out for minus 2 and 2, but this relationship is supposed to hold for all x. Or really, I should say, for all x for which these expressions are defined, which is the sort of thing I would write in careful detail in the book. But in this setting, I can afford to be a little sloppy. Anyway, so sure, this function g does the same thing to minus 2 as it does to 2. But do I know if it's going to do the same thing to minus any old thing as it will to that old thing itself? Yes, we could say that this guy is an even function because for any x, g of minus x is going to be, well, by definition, minus x to the 4th plus 3. But minus x to the 4th is the same thing as x to the 4th, of course, and the plus 3 comes along for the ride, and lo and behold, x to the 4th plus 3 is itself g of x. So we have shown that for all x, g of minus x is g of x. So yes, this is an even function. And there's more we could say about even functions. You may have met them before. The most interesting thing being that the graphs of even functions have a nice symmetry, because if f is some even function, that means that when I stick in any value x and it's negative, the value of the function that comes out will be the same. So if the value of this input is whatever that is, I'll get the same thing over here. When I pop its negative in, I get the same output. Since that's going to happen anywhere, the graph of any even function is always going to have this nice symmetry. It's going to be symmetric over the y-axis, but that's not particularly important to us today. Mainly, I just want you to know what an even function is, because many functions we will be considering in this class are even. But before I mention them, we should also define what is meant by an odd function. A function f is said to be odd if a different kind of relationship holds between f of minus x and f of x. Namely, if they are always equal but opposite, at least whenever these expressions are defined. Some examples here. How about f of x is x cubed? It's odd because if you stick a number and it's negative in, you will get opposite outputs. If you cube 2, you get 8, but if you cube minus 2, you get minus 8. You cube negative 3, you get minus 27, which is the opposite of what you'd get if you cubed 3. And of course, it's clear why that happens. The cubing function is odd because for any x, f of minus x is the cube of minus x, and by basic algebra, that is minus x cubed. And since x cubed is f of x itself, this is minus f of x. Since f of minus x is minus f of x, for all x, this is indeed an odd function. Odd functions have nice graphical properties as well. If g is an odd function, that means for any input and it's negative, the outputs will be equal but opposite. And since that's going to happen everywhere, then you get a nice kind of symmetry, which is sometimes described as symmetry about the origin. Because if you take any point and fire it into the origin, then it's going to come out on the other side the exact same distance and be back on the graph. But again, I'm not too concerned about the graphical interpretation of odd functions. I just want you to know the definition. The important thing for us is that almost all the functions we meet in trigonometry are either even or odd. This isn't true of most functions in general. Most functions are neither even nor odd. These are special properties. But let's consider our favorite trig functions. Is sine an even function or an odd function or neither? Well, think about the unit circle. If I have some input theta and it's negative minus theta, what can I say about sine of minus theta versus sine of theta? Well, sine of minus theta is the y-coordinate of this point. Sine of theta is the y-coordinate of this point. Clearly, those y-coordinates are equal but opposite. So that means that sine is an odd function. So I'll record that here. Or how about this? Is cosine even, odd, or neither? Well, look at the exact same picture. Cosine of minus theta is the x-coordinate here. Cosine of theta is the x-coordinate here. Clearly, they have the same x-coordinate, no matter what theta is. So that means cos is even. And what about tangent? Well, again, just think of the same picture. Here's minus theta, here's theta. Tangent is the slope of this radius. Tangent of minus theta is the slope of this radius. Do they have the same slope? No. These slopes have the same magnitude, but opposite sign. This is a positive slope, this is a negative slope. But if the slope here is, say, 2, the slope here is minus 2. So is tangent even, odd, or neither? It is odd. Good. These are important facts. And we can record them as follows. For all theta, cosine minus theta is the same thing as cosine theta. Now, we don't memorize it in that form. We just remember that cosine is an even function. And this is useful to remember in many contexts. Even just writing down something like, oh, what's the cosine of minus 150 degrees? The first thing we might think is, well, cosine is an even function. That means it absorbs that negative. It might as well not be there. So we could say the cosine of minus 150 is the cosine of 150, since cosine is even, and then we don't have to worry about that pesky negative anymore. We can just think, well, what's the cosine of 150 degrees? Well, that's 30 degrees shy of a half turn, so I have my reference angle of 30 degrees. Cosine of 150 is the x-coordinate of that point. Cosine of 30 is the x-coordinate of that point. Clearly, those are equal but opposite, so cosine of 150 is minus the cosine of 30 degrees. And cosine of 30, what's that? Well, we use our cofunction identity. Cosine of 30 is the same thing as sine of 60. And everybody knows that sine of 60 is root 3 over 2. That's just one of those ones you memorize. Good. Similarly, coming back to what I was writing at the top, for all theta, sine of minus theta is minus sine theta. Again, we don't remember it in that form. We just know that that means that sine is an odd function. And because we know what an odd function is, well, we know what that means. And that has nice uses. For example, if we wanted to know sine of minus 30, well, we would know immediately that that's minus sine 30, since sine is odd, and sine 30 is one of those ones that everybody knows. That's a half. So sine of minus 30 is minus a half. Good. And of course, we also saw that tangent of minus theta is minus tangent theta, which we don't remember in that form. We just remember that tangent is an odd function. And I won't write out a specific example with tangent. I will just point out that I have sometimes told students that if you know how to work out, say, the secant of minus 210 degrees and understand every step involved, you know a fair bit of trigonometry. So let's just do that to finish this off. What is the secant of minus 210 degrees? And you might say, well, wait, I don't know if secant is even or odd or whatever. Doesn't matter. Just turn it into a question about cosine, because you know about that. We know secant minus 210 is 1 over cosine minus 210 by the definition of secant. Now, what about cosine minus 210? Hey, cosine is even. That means it absorbs that negative. And that gives us plain old cosine of positive 210. That's a lot nicer to work with. That's because cosine is even. Now, what about cosine 210 itself? Well, there I just have to think about the unit circle. 210 degrees. That's 180 plus an additional 30. So my reference angle is 30 degrees, and I just have to think cosine 210. Okay, that's the x-coordinate at that point. How does that relate to the x-coordinate at this point? Clearly, those are equal but opposite. So cosine of 210 is minus the cosine of 30 degrees. And now what? What's the cosine of 30 degrees? Well, use your cofunction identity. Cosine of 30 degrees is minus sine of 60 degrees. Or rather, cosine of 30 degrees is sine of 60 degrees. We're just dragging that negative along for the ride. Sine of 60 degrees, everyone knows, is root 3 over 2. So that gives us 2 over root 3, or if you like, 2 root 3 over 3. And we are done. Notice how many little things we used, how many trigonometric facts we used here. We used the definition of secant. We used the fact that cosine is even. We used a cofunction identity. We used the fact that sine of 60 is root 3 over 2, which we understood from our 30, 60, 90 triangle as half of an equilateral triangle. We used the unit circle definition of cosine to get that cosine 210 in the first place. There's a lot going on. The important thing here is not knowing what secant of minus 210 is. And actually, as I do this, I see that I dropped a negative, so let me restore that. The important thing is understanding all those pieces. This is a good exercise not because the world needs you to be able to figure out what secant of minus 210 degrees is. This is a good exercise because the world needs you to have a good grasp of trigonometry and the relationships among the functions that drive trigonometry. Okay, that's a good place to stop. And this laptop is running out of juice, so excellent timing indeed. All right, see you next time in Chapter 11.